Good morning. Today we are going to discuss about the convection. So first let us discuss about the definition of convection once again. Convection means heat transfer by means of mixing of molecules. So already we have discussed in the introduction that convection is two types. First one is natural convection and the second one is forced convection. So natural convection means natural convectional currents are going to form and they causes the mixing of molecules and they causes heat transfer. As well, forced convection means by agitation or by means of any mechanical means we are going to mix the molecules and we are going to cause the heat transfer. Such a kind of process is called as forced convection. So let us discuss whatever the different kinds of heat transfers by means of convection. So under which let us discuss first about the heat transfer by means of a metal wall into the two kinds of liquids. One is warm liquid which is having a close contact with the metal, as well as from that metal how the heat transfer takes place to the cold surface. So let us discuss about the same. See, this is the warm warm water, okay, which is having contact with the metallic wall. This is metallic surface, as well as and this metallic wall is having close contact with the cold fluid. So here whenever we are going to place the metal in between the warm water as well as cold water, here cold water forms like a film, that is B1, B2, as well as warm water forms like a film A1, A2. So here what happening is, whenever warm water is having a certain temperature, that temperature is going to permeate through the warm water film, that is A1, A2, and that heat permeates through the metallic wall, as well as that may permeate through the cold water film into the cold water. So this is bulk of the hot water or warm water, and this is the film, and this is the metallic walls of one side to the another side, and this is the cold water film, and this is the bulk of the cold water. Generally this is the what is the total structure of the heat transfer process from hot water to the metallic wall through the cold water. So let us discuss here a maximum temperature T1 of warm water, that the heat which is permeates with a certain temperature, that is nothing but T1, through the A1, A2 film. Okay, that means here with T1 it permeates through the warm water film with T2 temperature, as well as from this film again it permeates through the metallic wall with temperature T3, as well as it flows from one end of the metal wall through the another end of the metallic wall, that means having temperature T4, as well as after permeating through the another end of the metallic wall, again it permeates through the cold water film, that is B1, B2, with a certain temperature, that is nothing but T5, and as well as finally it reaches to the bulk of the cold water with T6. So the permeation of a heat with a certain temperature T1 from warm water, and finally it permeates into the cold water with a certain temperature, that is nothing but T6. So how we have to write the rate of heat transfer through all these areas, that means bulk of the warm water, as well as through the warm water film, as well as through the metallic wall, as well as through the cold water film and as well as into the bulk of the cold liquid. Let us see. See, how can we write the equation of heat transfer through the warm side? So, rate of heat transfer is depicted by means of Q, and already we have studied that where rate of heat transfer is equal to thermal conductivity divided by thickness of the film. So, here thickness of the film is nothing but the thickness of the warm water film is called as x1. So, K by x1 as well as surface area is called as A, and temperature gradient, that means the temperature difference between the T1 to the T3. See, where T1 is having more temperature as well as T3 is having less temperature. That's why what we are going to do, we are going to write the equation in such a way, T1 minus T3. So, as we know that H is called as resistance. Okay, resistance is equal to thermal conductivity divided by thickness. So, if you substitute this one into the equation, then equation turns to H1A into T1 minus T3. That means temperature gradient through the warm water to the warm water film. So, in such a way we can write the equation. So, let us simplify this, let us write the equation once again, where Q is equal to H1A, okay, T1 minus T3. This is the equation which one we are going to use for the heat transfer through the warm side. So, let us discuss about the heat transfer, rate of heat transfer through the metallic wall. So, again here we have substituted thickness x1 for thickness of the film, that means warm water film, and here we have to substitute the thickness of the metallic wall. Okay. So, here it is xw, thickness is xw, that's why we are going to substitute the same. So, where Q is equal to kw xw into A into T3 minus this is T3 minus T4, T3 minus T4 temperature gradient. Why? Because T3 is more than T4, that's why we are going to write the equation in such a way. So, T3 minus T4, in such a way we are going to write the equation. So, let us write the heat transfer through the metallic wall, that is this one, that is equal to kW by xw. You need not to write this W. So, let us write the equation once again. So, that is equal to K by xw into A into T3 minus T4. This is the rate of heat transfer through the metallic wall. So, we can write the equation in such a way. Okay. So, coming to the cold side, that means this side, how the heat transfer is going to occur. So, here the film thickness is x2. This is a warm water film, that means A1, A2, for the thickness is x1, okay, as well as this is a metal wall thickness, okay, that is x3, as well as this is the cold water film, okay, that is x2. So, that's why we are going to substitute over here. Then overall heat transfer is equal to Q is equal to K by x2 into A into T4 minus T6. This is the gradient. So, here we are going to write in such a way. T4 is greater than T6. That's why we are going to write the equation in such a way. So, here in such a way we can write the equation where H2 where K by x2 is equal to the H2. That's why this one we are going to substitute over here, and finally we are going to write this equation where Q is equal to H2 into A into T4 minus T6. So heat transfer through the cold surface, we can write down it as Q is equal to H2 into A, okay, into T4 minus T6, such that what we can do, we can write the equation. So Q is equal to H1A into T1 minus T3 is the equation for rate of heat transfer through the warm surface, as well as Q is equal to K by XW into A into T3 minus T4 for the equation for heat transfer through the metallic wall, as well as in the cold side Q is equal to H2 into A into T4 minus T6, like that we can write the equation. Now let us write overall heat transfer. That means overall heat transfer Q is equal to, so here how we are going to write the equation? Resistance. Resistance into surface area into temperature gradient. In such a way we are going to write the equation. So if we remember the previous equation, that is equal to Ka delta T, like that we have written the equation. So here how we can write that equation, where Q is equal to H1 plus XW K by XW plus H2 into A into T1 minus T6, where all this is called as resistance, okay, as well as you can write it as overall resistance, that is nothing but U, overall resistance. That's why U is equal to H1 plus, okay, KW by XW, that means K by XW plus H2. In such a way we can write the overall heat transfer coefficient, overall heat transfer, overall resistance U, okay. So now where we know that Q is equal to overall heat transfer is equal to, where resistance is termed as U, overall resistance is U, that means this one. So this covers all, as well as A means surface area, okay, as well as temperature difference, T1 minus T6 we can write it as delta T. So how we can write this equation? Overall heat transfer through the metallic wall from warm region to the cold region, you can write it by means of Q is equal to UA delta T. So in such a way we can write the overall heat transfer process through a warm surface by means of a metal wall into the cold water. Coming to the next topic, boiling of liquids in a tube. So boiling of liquids in a tube or heat transfer in a boiling tube takes place by three mechanisms. First one is pool boiling, second one is boiling in vertical tube, and third one is forced boiling. So three kinds of heat transfers takes place in boiling of liquids. So let us discuss them individually, under which first one is pool boiling. Pool boiling means boiling of liquids by means of a metal, say by means of water heater. So let us discuss in this one how the boiling is going to happen. So we can discuss it by means of a simple graph which is constructed by using temperature difference on x-axis as well as heat flux on y-axis. So here when we are going to place a water heater in the cold water, and if we are heating the contents, then what happening there? Initially the rate of heat transfer is a little more, because the temperature difference between the wall of the water heater as well as cold water is more. That's why here initially the raising in the heat flux is going to happen. So later on, usually already we have discussed the rate of heat flow is directly proportional to the temperature difference. So further, the heat flux is reaching to the maximum because of whenever you are going to heat the water heater with the help of electricity, usually its temperature is going to increase more. So here what happening there, at that particular time of point, the difference between the temperature of cold water to the wall of the water heater is more. That means delta T is more. See, up to a certain point, the delta T is going to increase enormously. That's why what happening there, usually the enormous heat flow is going to occur. So after reaching to a certain point such as this point D, where the temperature of the metal wall as well as water is going to reach to the same temperature. That means the temperature difference between the wall of the water heater to the cold water or water is going to be equalized. That's why what happening there, further the heat flow is going to be decreased. So this one, where A to B, the rate of heat flux is more or is going to increase little, further it is going to increase enormously, later on it is going to decrease. So initially the temperature difference is more, that's why the rate of heat transfer is more. After that, after reaching to a critical point, its heat flow or heat flux is going to be reduced due to the reduced delta T. Okay, so here AB, here little increase in heat flux is going to happen. Okay, after that BC is called as nucleate boiling region. That means boiling of water with the help of this water heater is going to happen, where the temperature or the heat flux is going to be more with the boiling. That's why nucleate boiling region, like this we are going to call this what is that area. As well as when it reaches to the sea, okay, the rate of heat flux is going to be more. So here the C is called as critical boiling region, or after this region the temperature drop is going to happen. That's why you can call it as critical temperature drop also, temperature drop point also, like that we can call this region. So after C, the rate of heat flux is going to decrease. Why? Because the temperature difference is going to decrease. That's why the rate of heat flux is going to decrease. So initially the rise in temperature is because of temperature difference, initially the rate of heat flow is going to increase because of delta T is more between the cold water to the heater. Later on, by heating the heater, rate of heat flow is more, but at a certain point both that means heater wall as well as cold water reaches to a certain temperature, that means equal temperature, there is no further heat flux is going to happen. That's why decrease or it may reaches to the saturation is going to happen. In such a way pool boiling is going to happen. Coming to the boiling in vertical tube, in boiling in vertical tube, initially at the base of the tube, in the vertical tube, the rising of boiling water is suppressed by means of head which is present at that above base. That means liquid arranges in different layers. So rising of one layer is suppressed by means of which are the layers which are present above that layer. So in such a way, here initially boiling is suppressed by means of the head. Head means whatever the layers which are present above the underneath layer. Okay. Later on, if you are going to produce the heat to the water, that means you are going to supply heat for boiling of the water, then this water gains the heat and bubbles are going to form. Bubbles are nothing but air pockets are going to be formed. So these air pockets are going to flow like natural currents, and they are going to supply the, or they are going to mix the what is that layers, by which means they are going to supply the heat. Already we have discussed. Convection means mixing of molecules leads to the heat supply or heat flow. So here bubbles are going to form and they are going to supply the heat from lower layer to the upper layer, as well as upper layer to the lower layer, or by means of convection the heat supply is going to, or heat flow is going to happen. So this particular formation of bubble, this particular point is called as bubble formation. So later on, if you are going to supply the heat, the bubbles get coalesced, as well as large size bubbles are going to form. If you look at this one, small size bubbles are going to be formed with the absorption of heat. Later on, bubbles get coalesced. So the coalesced bubbles are called as slug. So that is called as slug formation. Here slugs are going to be formed. So here heat flux is going to be increased with all the formation of what? Such a kind of fluid dynamics. Okay. Further these bubbles, large bubbles get coalesced and they forms like a large slug, large bubble, that is called as slug. So here likewise the slug is going to be formed, and as well as whenever further you are going to supply the heat, so the slug is going to be carried upward to the, what is that, upward to the vertical tube. So here in such a way, why they are going to be carried such that, so vapor pressure within the slug is going to be increased. The vapor pressure is going to drag up the slug through the what is that vertical tube. In such a way it is going to happen. So finally what happens further, if you are going to supply the heat, okay, then what happens? Usually the slugs are going to be break down, and annular flow of liquid through the walls is going to happen in such a way. So this is called as breaking of slag or breakdown of slag, and this is called as annual flow of the liquid. So further if you are going to supply the heat, so whatever the liquid which is flowing through the wall, that acts as a film. Okay, usually film is the resistant layer for the permeation of heat through the what is that film into the bulk of the liquid. That's why here what happening there, rate of heat flux is going to decrease at this point. So further what happens, if you supply the heat, okay, the annular film will get evaporate and it forms like a dry spot, and which is the great resistant layer for the further heat flux into the liquid. So here what happening there, likewise, okay, here little formation of bubbles increases the heat flow, as well as formation of slugs will decrease the heat flux, and breakdown of the slugs further decreases the heat flux. Annular flow also decreases the heat flux, because annular flow means the flow of liquid forms like a layer, and that is the resistant layer for the supply of heat. So further if you are going to supply the heat, there is no increase in the temperature of the liquid. So if you evaluate the temperature, so initially the temperature is going to rise in such a way, okay, then later on there is no increment of the temperature, that means that reaches to the saturation. Okay, why? Because the what we call the rate of heat flow is directly proportional to the delta T. So, difference in the temperature is the driving force of heat flow. So, if it is going to be decreased, there is no heat flow further. In such a way, we can study about the same. Coming to the third one, forced boiling. Forced boiling. As we know that by means of agitators, that means mechanical agitators, okay, with the application of heat to a liquid within a boiling tube, what we can do? We can increase the heat flow. So, if you increase the heat flow with the help of agitation or mixing of the liquid by means of a stirrer or by means of an agitator, whatever it may be. So, it is called as forced boiling. So, in such a way, the rate of heat flow is going to be increased. So, if you compare all these three, okay, the final one is having more heat transfer, that means heat transfer coefficient. Why? Because if you are mixing it well, the rate of heat transfer is more. In pool boiling as well as in boiling in vertical liquids, natural convection is going to happen. That means natural convection is the mechanism of heat transfer. But in forced boiling, okay, the forced convection currents are going to be formed with the help of agitator or stirrer, okay, that enhances the rate of heat flow. So, when you are comparing all these three, forced boiling, okay, is the very effective mechanism of rate of heat transfer.